Yes. All right, good morning, everyone. Welcome back to another exciting day in mathematics. Whoop, whoop. Warm-up 77's on the screen, and Ulisa's already here, so we can get started now. By now, you should be able to do that by yourself. For number 2, remember, practice completing the square. Even though we can solve it another way, but do the process of completing the square. I'll give you guys some time. Ready and go. All right, let's get the show on the road. Once again, by now, number 1 should be automatic since we've been doing this already for a couple of weeks and it was part of your home play last night. So what you get for the sum? Let's go with Kelly. What you get for your sums, Kelly? 22 plus 2i. Hands, have you got that? That is correct. Pass on one for the difference. What'd you get for the difference? Caitlin. -8 plus 8i. That is correct. Hands, have you got that? Let's go. Let's go to the product. Show your neighbor what you got for the product really quick before Caitlin passes it to someone. Product. All right, Caitlin. Joseph, what'd you get? 120 plus 54i. Hands, have you got that? Looks about right. Double check your work. Let's go to number 2. I'm going to solve that by completing the square. I'm going to go through the entire process really quick just to make sure you got it. And by now we should be experts at completing the square. I'm going to do it all in black. By now we should know the difference for each step, yes? So step 1, standard form, equal to 0. Step 2, divide by the leading coefficient. Step 3, eliminate the constant. Step 4, complete the square, plus -4 over 2 squared to each side. -4 over 2 squared. X squared minus 4x plus 4 equals to 12 plus 4, which is 16 on this side. X squared minus 4x plus 4. Factor. Square root and square root, that is x2, sign of the middle, all that equal to 16, or we can write it as x minus 2 squared equals to 16. Next, square root to each side. That gives us x minus 2 equals plus minus 4. From there we add 2 to each side, so we end up with x equals 2 plus minus 4. So my two equations, x sub 1 is 2 plus 4, which is 6, and x sub 2 is 2 minus 4, which is -2. Hands, have you got that by yourself? Let's go. Once again, I'm giving you plenty of practice with completing the square, guys, because it's coming up, and I'm thinking by next week. Imagine doing this, look up, all this, but twice at the same time with 2 different variables. Ooh. Oh yeah, we got this, Caitlin. Let's go. Number 3, show your neighbor your graph for number 3, see if it looks something like yours. All right, here it goes. I got x over here, f of x over here. So to graph f of x equals x squared without a table, I start at -2. What is -2 squared? 1, 2, 3, 4. What is -1 squared? 1. 0 squared? 0. 1 squared? 1. 2 squared? 4. Whoop. That's my f of x. Then we need to substitute these values into our general rule. So 1 there, 1 there. negative 4 there, and 5 there. So my new rule is g of x equals 1 times f of 1 over 1x. Negative 4 times the negative is positive 4 squared plus 5. However, I said we're no longer going to use the 1s or the f. So g of x equals x plus 4 squared plus 5. Some of you are wondering, where did the 1 go? Well, this one and the f, I'm no longer using them, and 1 over 1 is 1. It's invisible there. However, tell your neighbor where we're going to move these 5 points to according to that. We're going to move them to. All right. Joseph, pass someone. Elijah. 4 to the what? 4 to the left. And 5 up. Hands if you agree with that. That is correct. Now check this out. Look up to the screen. They're asking us, or Mr. Q is asking you, to use the vertex of the original. What is the vertex? 0, 0. So I'm going to take 0, 0, and I'm going to move it 4 to the left and 5 up. 4 to the left, 2, 3, 4, 5 up, 4, 5, which is right there. So if you were to picture this whole thing, because I moved just this up here, it's going to be somewhere up there. And if you got that, all right, good. And last but not least, number 4, solve by substitution. So the first equation is y is equal to x plus 3. The second one, instead of writing y here, I'm going to write what? 2x plus 3. Bring down the equal sign, bring down the negative x minus 6. Get all the x's to one side, so plus x, 3x plus 3 equals 6. Leave x by itself, so minus 3 minus 3. 3x equals 3. Divide by 3. X equals 1. Now, when we have a system of 2 variables, we're going to end up with one point that has an x and a y value. So we already have our x. Now we need a y value. Which equation shall we use? The top equation or the bottom one? Okay. Top or bottom? Top. All right. I'm going to go with the bottom one. I'm just trying to prove a point that it doesn't matter which one you use. As long as you substitute the value, you're going to get the same answer. So y equals negative parentheses minus 6. And instead of the parentheses, I'm going to put a 1 for x. So therefore, this is y equals negative 1 minus 6. So y equals negative 7. Negative 7, this is my solution. And remind your neighbor what that means, according to what I said yesterday. What does this solution mean? All right. Looks like Ashlyn's got this one. Go ahead, Ashlyn. Where both lines intersect. That is correct. Let's go. So if I was to ask you to graph this and this, they're going to intersect at that point. All right, copy the agenda, please. Warm-up 77 is done. We're in the middle of complex numbers. And tonight, it's going to be a fun home play on electric circuits. Let's go. Tonight's home play, you're doing numbers 19 to 24 only. Make sure you get the practice in. And once again, if you guys are absent by any reason, Make sure you're going to the YouTube channel, watching the video lesson, and taking copious notes and doing your home play. Like I said, semester 2, concepts are going to start coming a little bit faster, so just giving you a heads up. All right, and to access the home play, here goes the code. 9NZV8. 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 All right. So, last night's home play were numbers 1 through 18. Go ahead and go to Canvas, turn that in. And I'm counting it as the pop party. How about them apples? Pretty good. Let's go. Thank you, Mr. Q. You're welcome. I got you. And tonight's home play looks something like this. Let me see. Like this. Look at the electric circuits. Let's go. And that. All right. After that, get a Cornell note ready, please. We're continuing on with our complex numbers. Complex numbers. Okay, we good? Yes, Mr. Q. All right, here we go. I can define and compute complex numbers. So, turn to your neighbor, let them know what complex numbers are in your own words without looking at your notes. What are complex numbers? All right, good conversation. Write it on your screen, please. What are complex numbers? Type it in there. 1. All right, something like this. 1 real and 1 imaginary, yes? Is that what you guys said? All right, very good. So, yesterday we covered examples that look like this. It was on your home plate where you labeled what each one was, yes? From there we went to these that we've been doing on the warm-ups, and yesterday was an easy transfer since you did that on your home plate. Yes? So far so good? Which brings us to this. Now, we started with electric circuits, and I introduced this portion where I showed you an electric circuit using a switch, a light bulb, and a battery, and how it looks in 2D, which is a sketch like this. So if I was to hire you guys this class, and ask you guys to package a switch like this, a battery, and a light bulb in a little baggie, and then ask someone else to do a diagram for it, this is what you will include so people would know how to connect it. And then we said that that was found in electronic devices. You copy this table, and we have how many components? 3, a resistor, inductor, and capacitors. Is that correct? Yes, Mr. Q. And the diagrams are here for each of those. The resistor, the symbol is like this. Why? Because we get that, and I mentioned that it's in between light bulbs. Now, some of you are like, what do you mean, Mr. Q? Yeah, originally light bulbs, let me elaborate because some of you haven't seen this before. You guys think that light just comes through the ceiling by itself. Light bulbs look like this. They have a base that's like this, and then the light bulb is made out of glass. Yes.
Yes, we do.
And then this piece in here has a little thin wire that looks like this. And that's the one that lights up when electricity is put to it. So therefore, this component creates light. That's why that's called the resistor. That's where we get that symbol from. From there, an inductor, I asked you guys that if you wanted to do an experiment at home, here's an experiment. Look up. you get to the garage, to your parents' tools, and get a nail. There's a nail. You guys see that? And then you go and find a wire. They usually have wires that have either red plastic around it or black or white. And then you start winding the wire around the nail like this. And you're going to end up with two wires like that. And then if you were to connect this wire and that wire to a battery, this becomes a magnet. And once again, we get the symbol of inductor because of the winding of this wire. Do you guys see that right there? Yeah? All right. Now, in all instances, from the light bulb to the magnet, electricity is going in one direction, sometimes in two directions. Therefore, in order to stop it, they have something called a capacitor. And that's why we use this symbol, because it's going from one side, and imagine the hand stopping it from the other side and going like this, and it stops it. And that's the symbol that we use for capacitor. All right? So, yesterday, I showed you guys a diagram, such as this one, and you are able to label what each of those is with the initial. Is that correct? So, on your screen, label what is what, please. Do that right now. All right? So, resistor, inductor, capacitor. Pretty straightforward, yes? All right, let's do it again. Here goes another one, a little bit more intricate. So, label that, please. Each component. Go with the initials. All right. Looks like we got this. So here's some of your responses. We got capacitor, resistor, inductor. Let's see. Oh, what happened there? All right, looks like we got it. Here goes another one. Label the next one, please. A little bit more intricate. Go. All right. Looks like we got it. Yes. RCRI. So far, so good. And one last one. There you go. Just so you can see the different looks of the diagrams. Label that. All right. Let's see. What? What? Okay, so you guys got to make sure that these are kind of like V's, whereas these are kind of like waves. My goodness. Bah. All right, I think we got it. So, that brings us to here. All right, writing utensils down, look up to the screen. Here's a quick intro to electricity. For those of you that might be wondering, we have two types of electricity. Oh my goodness. All right, so there's two types of electricity. I'm pretty sure you guys notice there's electricity on the wall, yes? And there's electricity in vehicles or batteries. Well, the electricity on the wall is known as alternating current. The electricity in cars or batteries or cell phones or anything that has a battery is called direct current. That's why when you guys mess around with direct current from the vehicle or from batteries, you don't get a lot of electricity to kill you. You get enough sometimes to shock you a little bit. Or has anybody done this test with those rectangle batteries? Have you put them on your tongue? Some of you? No? Come on. Don't tell me I'm the only one. Anyways, that's direct current. However, if you were to get a wire from the wall and put it on your tongue, you die. Because that one starts at 120 volts. It starts at how much? 120. Let me reiterate. Oh my goodness. It starts at 120 volts, alternating currents. Direct current starts at actually less than that, but usually at 1.5 volts, which is almost nothing. Car batteries are 12 volts. Tractor and bigger vehicle batteries, they put more than one battery together and they go anywhere from 18 volts up to whatever. But nothing compared to how much? 120. That's why since you were a kid, they told you not to mess around with the outlets. Is that correct? All right. So that's alternating. Now, why is it called alternating? Because the wall, look up, has something that looks like this. And many times when you plug in stuff, you don't really think about whether you're doing it upside down or right side up. Why? Because both of these have the same current coming through them, both positive and negative. That's why it's called what? Alternating. You can alternate the outlets. Whereas over here, the batteries, there's only a positive and a negative. And if you switch them, you burn stuff out. Straight up. So, how do we measure electricity or current going through something? It's called impedance. And the symbol that is used is this one for ohm, also known as the Greek letter omega. All right? Good intro? Yes, Mr. Q. All right, good. So, let me continue. So yesterday you got a table that looked like this. We're going to add a little bit more to it, so copy this one, please. On the left column, circuit component, resistor, inductor, capacitor, the symbol, there they are, and then here what it represents. Copy that. All right. Now look what each of these components turns into. Look up. And this is how we transform electricity into complex numbers. Ready? Look up. Don't copy this. I'm going to give you other words to write in there. But look, the resistor is a real number A. An inductor is an imaginary where B is greater than 0. And a capacitor is an imaginary where B is less than 0. In other words, write this down in there. A resistor is a constant. What is a constant? A number without a variable. An inductor is a positive imaginary number. And a capacitor is a what? Negative imaginary number. Once again, from now on, whenever you see on the diagram a resistor that looks like this, you're thinking that it's going to be just a number without a variable. Whenever you see an inductor, you're going to think of a positive imaginary number. And whenever you see this symbol for capacitor, you're going to think of a negative imaginary number. All right? Now, how does that translate into what we're doing, Mr. Q? Well, let me show you. Look up to the screen. Watch. Don't copy this. Just pay attention. Write your utensils down. Let's say I gave you this diagram. It's an electric circuit. Do you agree with that? All right. And we know now what each of those are. This is a resistor, this is an inductor, and this is a what? Capacitor. Are we there? So how does that translate into math, Mr. Q? Well, look at it. And look what each of those represents. Talk it over your neighbor. Let them know what would I write for resistor, for inductor, and for capacitor. Talk it over your neighbor. Now that they gave me some current that's going through them, what would I write for that? All right. Start with Enrique. What would I write for resistor, Enrique? The resistor being right here. 4. Hands if you agree with that. That is correct. So, what would I write for inductor, Edwin? 3I. Hands if you agree with that. That is correct. And of course, lastly, we have capacitor here. I would write negative 5I. Are we there so far? All right. So, with that said, copy this one on your paper. Not this one. This one. Example 5. Copy the diagram, the table, and fill it in, please. Make sure when you're about to label here your table, before that, label your diagram with the initials of each piece, so like that you don't get lost. All right. So I'm going to get you guys started with this one, and then Gio's going to enlighten us. So this one is our resistor, this was our inductor, and our capacitor. So what shall I write here? Negative 10. All right, hands if you agree with that. Very close. Tell your neighbor which one we need to change. Gio, which one shall we change? The 7 to a positive. That is correct. Yeah, we change it to a positive. All right, hands if you got that. All right, let's do another one. Copy that one, example 5Q. Copy the diagram. Then you're going to label it with the initials after you copy it, and then answer the question here, and I'll send you a screen. Go. All right. So, for the sake of time, let me go over this one. Gio, pass them one. Sean. So I got resistor, inductor, capacitor. So what'd you write for here? Hands, have you got that? All right. So from 1 to 5, how comfortable are you with this so far? Yeah, 5, 5, 5, okay. But what if I gave you this? Don't copy it. Look at it. All right. So by looking at it, tell your neighbor what you would write here, here, and here. Talk it over your neighbor. What would you write there, there, and there? All right. Looks like Mariah's got it. Very good, Mariah. Let's go with Renzo. Renzo, what would you write? Oh, let me label it first. We got capacitor, capacitor, resistor, resistor, and inductor. So what do I write here? 9, and here? 7I, and here? negative 5I. Hands if you got that. That is correct. And what are we doing? Whenever you see more than one, you just combine the ohms or the impedance. All right, once again, that's the impedance. That's how much is going through, flowing through there. All right, which arrives us to here. Copy this formula. V equals I times Z. We're going to be using this to compute the actual voltage going through each component of a circuit. V equals I times Z. The I stands for the current in amps. Current in amps. And you already know that the Z stands for the impedance, which is the one that we just did right now with all those numbers. All those numbers are known as what? Impedance. All right? So, let's do one like your home play. Ready? Copy this one down. Example 6. Example 6, I want you to write V equals I times Z. 24 plus 12I for your current. This is your diagram. Make a table like this. Hurry up, please. So, let's label our diagram. This is our resistor, inductor, capacitor. So with that, what do I write for the impedance? Impedance. What do I write here, Jesus? Go. 4, 3I, and negative 5I. Hands, have you got that so far? All right. So now we're going to figure out the voltage going through each component. Ready? So I'm going to use the formula V equals I times Z. So here we go. I'm going to write it here. V equals, for the I, I'm going to open a parentheses in red, and I'm going to substitute this value, 24 plus 12I, times the impedance. What is the impedance for this one? 4. So, here we go. To compute the voltage going through, I distribute the 4 in here and in here. So that gives me 96, sorry. 4 times 24 is 96, plus 4 times 12I, that's 48I. That is the voltage going through the resistor. Let's do one more. Let's do the inductor. Here you go. V equals, parentheses, 24 plus 12I times 3I. Here we go. Distribute. 3 times 24, that's 72I. 3I times 12I, that's 36I squared. Am I done up to right there? Look up. Tell you never what I need to do at the end. Substitute what for I squared? Negative 1. So this becomes negative 1 times 36 is negative 36. And then at the end we write plus 72I. That's the voltage going through the inductor. And you do the same for the capacitor, but instead of 3I, you substitute negative 5I. All right, I'm going to stop right there. That's exactly how the home play is going to go. They're going to give you something like this, and they're going to ask you to find the voltage through those components. Good one, everyone. Enjoy your home play. See you guys tomorrow. Bye. Bye. Have a good one.